This is the second part of lecture 3. In the first part of lecture 3, we have covered the topic theory and working of moving coil ballistic galvanometer. Since it's a lengthy lecture, we divided it into two. In the second part, we are focusing on figure of merit of BG and its determination. So, the first video, in that we covered the principle and construction of moving coil ballistic galvanometer. Then we looked through the theory and working of the ballistic galvanometer. And we went on and we also studied the correction for damping in the moving coil ballistic galvanometer. And with that we stopped the first video. And in this video, the second part of that, we are covering mainly the figure of merit of ballistic galvanometer. Before we go into that figure of merit, we will see this classification of this moving coil galvanometer. How we can classify the moving coil galvanometer into two. One is deadbeat galvanometer, other is ballistic galvanometer. The ballistic galvanometer we are studying in this chapter, but there is one more galvanometer, that is deadbeat galvanometer. What is deadbeat galvanometer? There is the moving coil galvanometer in which the coil is wound on a metallic conducting frame. In ballistic galvanometer, we are wounding that coil on non-metallic frame. But here in deadbeat, deadbeat is a moving coil galvanometer in that coil is wound on a metallic conducting frame. So it gives a steady deflection without producing any oscillation. And when a steady current is passed through the coil, it will produce a steady deflection. So what is deadbeat? Deadbeat is a different type of a moving coil galvanometer. In that, coil is wound on a metallic conducting frame, and here when a steady current is passed through that coil, it produces steady deflection. So it goes to one side and stops. It does not oscillate. Such a moving coil galvanometer we call it as a deadbeat galvanometer. So we will see what are the conditions that should be satisfied by a moving coil galvanometer to become a deadbeat or to become a ballistic galvanometer. So to become a deadbeat galvanometer, the moment of inertia of the system should be small. So that what will happen? So that the time period of oscillation will be small and there won't be any oscillation. Okay. So moment of inertia should be small and coil should be mounted on a conducting frame and the suspension fiber should be comparatively thicker. Okay, these are the three conditions we will mainly say for deadbeat galvanometer. If a moving coil galvanometer satisfies these conditions, then it will become a deadbeat galvanometer. And for becoming a ballistic galvanometer, what are the conditions that we already learned? Once again, we will go through that. That is, moment of inertia of the system should be large. Why? If it is large, then the time period of oscillation will be large. Okay. And the second condition that we learned is suspension fiber should be very thin. Okay. It should be very thin for the restoring that torque, and all for that condition, the suspension fiber should be very fine. And third one is the air resistance should be small and coil should be wound on a non-conducting frame so that damping is minimum. So in order to attain the minimum damping, the third condition says that air resistance should be small and coil should be wound on a non-conducting frame. So these are the conditions that should be satisfied by a moving coil galvanometer to become a ballistic, and the previous one for deadbeat. And these are the conditions that we say to classify the moving coil ballistic galvanometer. Okay, so galvanometer, moving coil galvanometer, one deadbeat galvanometer, one ballistic galvanometer. We in chapter ballistic galvanometer. So, deadbeat and ballistic opposite condition. Deadbeat galvanometer oscillate steady deflection moving coil galvanometer. Steady deflection main condition എന്ന് പറയുന്നത് എന്താണ് കോയിൽ എന്തിന്റെ മുകളിലാണ് നമ്മൾ ചുറ്റേണ്ടത് ഒരു കണ്ടക്ടിംഗ് ഫ്രെയിമിന്റെ മുകളിലാണ് അപ്പോൾ അതിന്റെ മുകളിൽ എന്തായിരിക്കും ഹൈ ഡാമ്പിംഗ് ഉണ്ടാവും ഹൈ ഡാമ്പിംഗ് ഉള്ളത് കൊണ്ട് തന്നെ അത് ഓസിലേറ്റ് ചെയ്യില്ല പിന്നെ അടുത്ത് നമ്മൾ പറയുന്നത് മൂവ്മെന്റ് ഓഫ് ഇനർഷ്യ ഓഫ് ദാറ്റ് സിസ്റ്റം അങ്ങനെയായിരിക്കണം, ചെറുതായിരിക്കണം. ചെറുതായുള്ള ഗുണം എന്താണ്? അതിന് ടൈം പീരീഡ് ഉണ്ടാവില്ല, ഓസിലേഷൻ ഉണ്ടാവില്ല. ഓക്കെ. ആൻഡ് പിന്നെ മൂന്നാമതായിട്ട് നമ്മൾ ഒരു കണ്ടീഷൻ കൂടി അവിടെ നമുക്ക് പറയാൻ പറ്റുന്നത്, ആ ഫൈബർ നമ്മളിങ്ങനെ തൂക്കിയിടുന്ന ഫൈബർ ഉണ്ടല്ലോ, നമ്മൾ ഈ ആ ഓയിൽ തൂക്കിയിടുന്ന ഫൈബർ എങ്ങനെയായിരിക്കണം? തിക്കർ ആയിരിക്കണം എന്നാണ് ഡെഡ് ബീറ്റ്. ബാലിസ്റ്റിക് നേരെ ഓപ്പോസിറ്റ് നമ്മൾ പഠിച്ച മൂവ്മെന്റ് ഓഫ് ഇനർഷ്യ വലുതായിരിക്കണം. അങ്ങനെയാണെങ്കിൽ അതിന്റെ ടൈം പീരീഡ് ഓഫ് ഓസിലേഷൻ ഹൈ ആയിരിക്കും. സസ്പെൻഷൻ പിന്നെ ഫൈബർ എങ്ങനെയായിരിക്കും? സസ്പെൻഡ് ചെയ്യുന്ന ഫൈബർ, ഈ കോയിൽ സസ്പെൻഡ് ചെയ്യുന്ന ഫൈബർ എങ്ങനെയായിരിക്കണം? വളരെ ഫൈൻ ആയിരിക്കണം. പിന്നെ എന്താണ്? നമുക്ക് ഡാമ്പിംഗ് ഏറ്റവും മിനിമം ഉണ്ടാവണം. ഡാമ്പിംഗ് ഏറ്റവും മിനിമം ഉണ്ടാക്കാൻ വേണ്ടിയിട്ട് എന്താണ് ചെയ്യുന്നത്? എയർ റെസിസ്റ്റൻസ് വളരെ ചെറുതുമായിരിക്കണം. അതുപോലെ തന്നെ അത് വൗണ്ട് ചെയ്യുന്ന ഇതിന്റെ മുകളിലായിരിക്കും, നോൺ കണ്ടക്ടിങ് ഫ്രെയിമിന്റെ മുകളിലായിരിക്കണം. ഇങ്ങനെയാണ് നമ്മൾ മൂവിംഗ് കോയിൽ ബാലിസ്റ്റിക് ഗാൽവനോമീറ്ററിനെ എന്ത് ചെയ്തിരിക്കുന്നത്? ക്ലാസിഫൈ ചെയ്തിരിക്കുന്നത്. ഈ കണ്ടീഷൻ നോക്കിയിട്ടാണ് നമുക്ക് പറയാൻ പറ്റുമോ അത് ഡെഡ് ബീറ്റ് ആയിട്ടാണോ വർക്ക് ചെയ്യുക, അതോ ബാലിസ്റ്റിക് ഗാൽവനോമീറ്റർ ആയിട്ടാണോ ഈ ഒരു മൂവിംഗ് കോയിൽ ഗാൽവനോമീറ്റർ വർക്ക് ചെയ്യാൻ നമുക്ക് പറയാൻ പറ്റും. ഓക്കെ. Now we will go to the two sensitivities, that is current sensitivity and voltage sensitivity of a moving coil galvanometer. Okay. Current sensitivity. We learned about this current sensitivity and all when we learned the conversion of galvanometer into an ammeter and voltmeter, and same method and we are following here also for calculating this sensitivity and all. Okay. What is current sensitivity? Current sensitivity means the current, minimum current that required to produce unit deflection in any scale. That's we will say as current sensitivity. Here we are using a what for measuring? What we are using? We are using a light and scale arrangement. So in the scale, that division is in millimeters. So here unit deflection will be 1 millimeter. So in this case, the current sensitivity is defined as current that is required to produce a deflection of 1 mm, 1 millimeter on a scale that is kept at a distance 1 meter from the mirror. So arrangement, I think you remember that arrangement. Otherwise we can go back and check that arrangement. Here is that arrangement. So there should be, here if you say this scale is kept at a distance 1 meter from this arrangement, and if it produces a 1 mm deflection, so how much current is needed to produce a 1 mm deflection on this scale which is kept at a 1 meter from this mirror? Okay, that current we will say that is the current sensitivity of that particular galvanometer. Okay, so current sensitivity S(c), we represent using S(c), is defined as current that required to produce a deflection of 1 mm on a scale. Okay, that scale is kept at a distance of 1 meter from the mirror. That amount of current we will say as current sensitivity of particular galvanometer. And usually it is expressed in microampere per millimeter because it's a small amount of current. So we will express in 10⁻⁶ ampere per millimeter. Okay, that unit that we use to express this current sensitivity. Similarly, we can define the voltage sensitivity S(V). It's a potential difference that should be applied to produce a deflection of 1 mm on a scale kept at distance 1 meter. So same thing here, we are in the current sensitivity we are considering current. In the other case, voltage sensitivity, we are taking the potential difference that we should apply to produce the deflection of 1 mm on a scale, that is unit deflection on a scale kept at a distance 1 meter from that mirror. And here also we express in microvolt per millimeter. The voltage sensitivity SV is expressed in 10⁻⁶ volt per millimeter. So how we will determine this? For that, the arrangement for determination of voltage sensitivity and the current sensitivity, the arrangement is shown here. Okay, the same arrangement you learned in the previous chapter when we looked for the conversion of galvanometer into a ammeter or voltmeter. Here we fixed the galvanometer there. Okay, and there we found out the current sensitivity K, and from that we found out the maximum the current that can be passed through that galvanometer Ig, and also we measured G. Okay, from getting that we assumed how much the value of S, that is small shunt resistance, that is needed to convert that galvanometer into a ammeter and all. The same arrangement we are using here. Okay, so what was the arrangement that we used there? There we have two resistance boxes, that is P and Q. Usually P will be a smaller resistance value. From the voltage across P is fed to the galvanometer. Okay, there also we did the same. So we have here also same arrangement. We have two resistance boxes, one P and Q. Okay, and that is connected. This P and Q is connected to an accumulator. That is the battery with a higher voltage accumulator, which is having EMF E, and there is a key K is there. Okay, and between the ends of P, that means from P we are taking the voltage, the potential difference across P is fed to the moving coil galvanometer. So between the ends of P, what is there? There is a resistance box R, and a galvanometer connected through a commutator. Okay, between the ends of P, a resistance box R is there, and what is there? There is a commutator. Okay, and through the commutator, what we are connected galvanometer for? Why we are using commutator? Commutator is used to if you keep it to one side, the current will flow into one direction, and if you keep the other, that we have a lock-like system. So using commutator, we can send the current to two different directions. Okay, so the commutator we are connecting it to moving coil galvanometer. Okay, this is the connection arrangement here. The thing why we are arranging like this, we want to take only the portion of PD which is applied across, which is acting across P to be fed to the galvanometer. So that's why we are doing the connection like this. So what we are doing is, first we will take a low resistance, very low resistance 1 ohm in P, and a high resistance 999 ohm in Q. That means we are keeping the total resistance P plus Q 1000 ohm here in this experiment. Okay, with no resistance in R. How we are starting? We are not keeping any resistance in R. That means we are not pulling out any resistance from R. We only took 1 ohm from the P, and we kept a 99 ohm in Q. Okay, and we are not keeping any resistance R. So what will happen? So current will flow through this. The current through this P and Q is same because this is in series. So if you put the key to the K and the connection is established, that means current will flow through this circuit. So current through this circuit will be E divided by P plus Q, and potential across P is E divided by P plus Q into P. Okay, current through this is, what is current through this? E divided by P plus Q, because this is a series circuit. If that is the current, if you want to find out the potential across any of the resistance, what you have to do, just to multiply this with that resistance. So potential across P will be the current through P into P. That is, current through P is E divided by P plus Q into P. That's the potential across P. That potential you are feeding to this region. Okay, so that potential is producing a deflection, the galvanometer, and you are not taking any resistance from R. Okay, so whatever the potential you are applying across P, that P is producing a deflection in galvanometer. Let it be theta. The deflection produced by the galvanometer will be theta. Due to the potential across P, that potential we fed to this, and that produces a deflection theta. That means EP divided by P plus Q produces a deflection theta. If you want to find out the voltage sensitivity, what is the voltage sensitivity? Voltage sensitivity is it is not the voltage to produce a deflection of theta, it is the voltage that required to produce, a potential difference that required to produce a deflection, unit deflection. So what you have to do, just divide by that angle. So voltage sensitivity SV will be the voltage across P, that is EP divided by P plus Q divided by theta, because this voltage produces a deflection theta. That is not the voltage sensitivity. What is the voltage sensitivity? That is the voltage that required to produce unit deflection. So what you do? Just bring that theta down. So that becomes the voltage that produces a unit deflection. So this is SV. Okay. There should not be any confusion. EP divided by P plus Q produces a deflection theta. Okay. That is not the voltage sensitivity. What is the voltage sensitivity? That is the voltage that required to produce a unit deflection. To make it unit deflection, you just divide that voltage divided by that angle theta. That will become the voltage that is going to produce the unit deflection. So EP divided by P plus Q by theta will give you SV. In order to express in microvolt, you just multiply with 10 raised to 6. Then this micro will cancel. You will get volt per millimeter. But we usually express in microvolt, so we multiply here 10 raised to 6. Okay. So in order to make it micro here, we multiply it. So this is the voltage sensitivity. This is the method to determine the voltage sensitivity. If you want to measure the current sensitivity, same method. What you have to do, the connections are same. Then you after determining voltage sensitivity, if you want to determine the current sensitivity, you just adjust the value in R. Earlier, when you are determining the voltage sensitivity, there is no resistance in R. Now what we will do? We will pull out some resistance from R. So we are introducing resistance in R, and you find out the value of R at which our theta become off. And this we learned earlier also. The value of R at which the deflection theta becomes half the value, that resistance will be always equal to the galvanometer resistance. Okay, that we already learned in the previous chapter. So what we are doing, after determining voltage sensitivity, we are slowly taking out the resistance from the R. Okay, resistance from the R we are taking slowly, and we are finding that the theta is actually when we are not putting R, it was theta. When started putting, that theta will definitely reduce, and at a particular value of R, you will get that theta equal to theta by 2. That value of R will be equal to galvanometer resistance Rg. So current sensitivity we can determine, you just divided by that galvanometer resistance. That will give you the, if you get the voltage sensitivity, if you want to get the current sensitivity of a particular galvanometer, you just divide it by the resistance of that galvanometer. That only we did here. Okay, and you change this volt to ampere. And 10 to 6 in order to cancel this micro. So this experiment we can repeat it for various values of P. Keeping, but we should keep P plus Q constant. That means we will always keep P plus Q 1000. You can take P1 first and you took 999 in Q. Next experiment you can take P equal to 2 ohm, you keep it at 998. That means P plus Q is constant. You can take 3 in P, 3 ohm in P, you can take 997 ohm in ohm. Like that, we can repeat the experiment so many times and we can get the values for current sensitivity and the voltage sensitivity. The value will be the almost same. Okay. So, that is how we will find out the current and the voltage sensitivity using this arrangement. Okay. Now we will go to the important part, the figure of merit of Vg. Okay. The measurement of charge sensitiveness. Okay, this charge sensitiveness is known as the figure of merit of Vg. Okay, so we measured the charge that is passing through the Vg, that is Q, and we got the equation as T by 2 pi C by NBA theta 1 into 1 plus lambda 2, because we are measuring theta 1 in the Vg. Okay, we will measure the theta 1, and in order to make it to equal to theta, this theta 1 is the with the deflection with the damping. So, but actual calculation we should get the theta is with the undamped, that is without damping. So, in order to go from theta 1 to theta, we have to multiply it with 1 plus lambda by 2. The lambda we already learned, that is a logarithmic decrement. That all we learned in the previous class. If you are not remember, you can go to the previous video and check it. Okay, so K here we can make that theta by 2 pi C into NBA, theta 1 1 plus lambda by 2, theta 1 1 plus lambda by 2 kept there, and T by 2 pi C by NBA we can call it as K. This K is the charge sensitivity, charge sensitiveness of that Vg, or we will tell that K as figure of merit of the galvanometer. Okay, it is also known as ballistic reduction factor of the Vg. That we learned in the previous lecture also, previous video also. Here, what we are going to measure is this charge sensitiveness. And what is this charge sensitivity? Okay, so this charge sensitiveness is known as the figure of merit of Vg. If you get a question, write the charge figure of merit of Vg, you should start from here. Okay, so figure of merit of Vg means charge sensitiveness of that Vg. What is charge sensitivity? Sensitivity that K means. This means that how much charge, that otherwise the charge that should pass through the coil means the galvanometer coil, to produce an undamped throw of 1 mm in the spot of light on a scale placed at a distance 1 meter from the mirror. It is same as our current sensitivity. What current sensitivity? Current sensitivity is the current that required to produce a deflection of 1 mm on a scale placed at a distance 1 meter from the mirror. The same thing here, the charge, the amount of charge that should be sent through that coil to produce a deflection of 1 mm on a scale placed at a distance 1 meter from the mirror. Okay, to make it more complete, we defined it as like that, the charge that should pass through the coil to produce an undamped throw. Okay, previous class also we are telling the undamped throw. We will mention there. If you wish to mention undamped throw there in the current sensitivity also, you can mention. But here we are making it more complete. We tell that produce an undamped throw of 1 mm in the spot of light. Okay, because spot of light is moving on a scale placed at a distance 1 meter from the mirror. You can also write it like this: the amount of charge that should be passed to the coil to produce a throw of to produce a deflection of 1 mm on a scale placed at a distance 1 meter from the mirror. Both are same. Okay, if you can write more in a more complete way, you can use the statement that given there. Otherwise, you can use the statement same as the current sensitivity. You just change the charge there. Instead of current, you put charge. Okay. So how we can measure this charge sensitivity? So here what we should measure is charge. So in order to get the charge, in order to store the charge or restore the charge, we should use a capacitor. So in the circuit, whatever we used earlier, the same circuit, same type of circuit we are using, instead of resistance R, here we will get a capacitor. Because this capacitor we are using to store that charge that is produced, that we can get from the potential across P. Here we are not applying that potential across P directly to Vg, because that time we are applying a voltage. Here we have to get the charge. So in order to convert the potential difference across P to charge, what we use? We use a capacitor here. So in order to do that, some changes we have to do in the setup, whatever we used in the earlier case. So what here, the first connection is same as that, and here we are just using AC. You can use E also. This AC I used to show the accumulator. This is shown in your book for study. That's why I used this one. Two resistance boxes P and Q, okay, and a key K, okay, is connected in series with an accumulator of EMF E. The same thing that we used in the previous one for measuring the sensitivity, current sensitivity, voltage sensitivity. Whatever circuit you used, the same thing is here also. But there we used a resistance box and then we connected to BG through the commutator. Here we are using a capacitor. Okay, we are using a capacitor of a non-capacitance C. Why we are using a capacitor? Because we have to store the charge and discharge the charge to find out how much charge should be sent to the coil to produce a unit deflection in this BG. Okay, so a capacitor C is connected to P, okay, through a vibrator V and a charging terminal CH, okay, of the charge discharge key. Here we have a charge discharge key is there, okay, which is having two terminal. One is charging terminal that I shown using CH, and other discharge terminal that I shown is DH. That DH is connected to one of the point of a commutator. This is commutator. These 4 points that I shown the commutator that I am representing using CR. Okay, so this capacitor is connected across P through a vibrator V. Vibrator we are using for to make a discharging and discharging connection with this charging discharging key. Okay, so it is connected through a vibrator and a charging discharging terminal CH. Okay, CH of the charge discharge key. Okay, charge discharge key. Setup is very simple. Okay, don't confuse. Instead of R, you put a C here. You need a vibrator here. You have to have a charging discharging point, so you have a charging terminal and a discharging terminal. Charging terminal is connected to P and discharging terminal is connected to CR, because in order to do the charging we want to take the potential across P, so connection should be across P. That connection is here. Okay, So the capacitor C is charged with the potential difference across P. Okay, charge on the capacitor is, then what we will do after charging, we will disconnect from here. The vibrator is disconnected from here. Then it is controlled discharge key, discharging terminal of charge discharge key. Okay, after charging, charge on the capacitor is discharged through BG. Okay, through BG using vibrator and discharge terminal of charge discharge key. Okay, so this is the setup we are using and how it is functioning. And we have a commutator. Why we need a commutator? We need a commutator because commutator is to reverse the charge in the BG, or we reverse the current through that BG, ballistic galvanometer. Okay, so we will start how we will do the experiment. Here, instead of 1 ohm in the P, we are taking 1000 ohm. Okay, and Q is kept at 9000 ohm. So our total P plus Q is 10,000 ohm here. The previous case, in the case of when we are measuring voltage and current sensitivity, where P plus Q was 1000 ohm, where we took P as 1 ohm, starting 1 ohm, and here we took at 999 ohm. But here it's a large value. In P also we are taking a large value, that is around 1000 ohm, because that charging capacitor can be done using a larger potential difference across P. Okay, so what we do is we first take P 1000 ohm in P and 9000 ohm in Q. Okay, here 1000, 9000. Then we will establish this connection first. Then what will happen? The current will flow through this. So current across P is E is the EMF I took, E divided by P plus Q is the current through this. Potential across that is E divided by P plus Q into P. That EP divided by P plus Q is the potential across this P. Then what we will do is we will connect this is not connected. We will connect this vibrator and this charge discharge terminal. Then what will happen? This potential that is developed across P is used to charge this capacitor C. So capacitor gets charged. Immediately what we will do? We will disconnect this terminal, and this is connected, this vibrator is connected to discharge terminal. Okay, discharge terminal of charge discharge key. Then immediately this capacitor will discharge through this way to this BG. So then BG will not a deflection, that there will be a throw is noted in BG. That throw we can tell as theta 1. First throw theta 1 is noted. And we will also note theta 11. For theta 11 also we will note that, because theta 11 is needed for finding out the logarithm decrement. So what we are doing is we are taking 1000 ohm in P and 10,000 ohm in Q, and we will start that first. We will set up a potential difference across P. That P is used to charge the capacitor. Immediately charging, we will discharge it through BG. Then we will note the first throw theta 1 and theta 11 also we noted. Okay, then we will find out the mean value of P by theta 1. Mean value of P by theta 1 is noted and kept. Okay, and we also get the value of theta 1 by theta 11 for all. Theta 1 by theta 11 also we will noted. Okay, theta 1 by theta 11 is needed for this one. Theta 1 by theta 11 also we noted for every value of P and Q. Then after first experiment, we will make P to 2000 and Q to 8000, and we will keep P plus Q as 10,000. Again, we will use the potential across P and charge the capacitor, and immediately we will discharge through VG, and we will note the first throw theta 1 and 11th throw theta 11. We will find out P by theta 1 for the second one, and also we will find out theta 1 by theta 11 for the second value, that's for 2000. Then we will go to 3000. We will keep the resistance value 3000 in P, and like that we can do a number of experiments. You can do 10 or 11, how many you want, you can do that experiment. Okay, so that is the way in which we will perform the experiment. Now how we will do the calculation? Let the capacitance of capacitor that we used to be C microfarad. We are thinking that we took a capacitor which is a capacitance C. Okay, C microfarad, not 10 raised to minus 6 farad. Then charge on the capacitor. We know that the charge on the capacitor Q is equal to C into V. You know that the charge that can be stored by a capacitor will be equal to the capacitance of capacitor and the potential difference that we established across that capacitor. Okay, here, sorry, Here, in this case, the potential that we are using is potential difference across the P. So that potential is EP divided by P plus Q, because the E is connected in series with P plus Q. So current through the P is E divided by P plus Q. Potential across P is equal to current into P. That means E divided by P plus Q into P. That is EP divided by P plus Q. And charge, we know that should be multiplied with a capacitance value. That capacitance, so we are using of a capacitance is C. So you multiply this potential EP divided by P plus Q with C. That will give you the charge. We are using microfarad capacitor, so the charge stored will be microcoulomb. And since microfarad, it will be microcoulomb. Okay, this charge produces a throw theta 1. This is the damped throw. In order to make it undamped throw, what you have to do? You have to multiply that theta 1 with 1 plus lambda by 2. That we already know, the damping correction we should do. So this charge Q produces a deflection, that undamped deflection of theta 1 into 1 plus lambda by 2. Okay, this is the relation. Now we know that K, what is K? K is the charge that required to produce unit deflection. Charge that required to produce unit deflection. If you multiply this K with theta, you will get the charge that produces the deflection theta, isn't it? Charge required to produce unit deflection is K. If you want to get the charge that produces the deflection theta, what you have to do? You multiply this K with this theta. So K into this theta, that is theta 1 into 1 plus lambda by 2, will give you the charge. Okay, that the charge that produces the deflection, this one, theta 1 into 1 plus lambda by 2. We know that, I think what I am telling you are getting. Okay, what I want to relate this K to this we are getting through the experiment, and we have to get the value of K. So I have to relate it to this. What is K? K is the charge that produces unit deflection. Okay, if you multiply this K with theta, what K theta gives the charge that produces the deflection theta. But we measure theta 1, so we have to multiply K with theta 1 into 1 plus lambda by 2. This will give you the charge that will produce the deflection theta 1 into 1 plus lambda by 2. That charge is Q. So I can write this K into theta 1 into 1 plus lambda by 2 is equal to EP divided by P plus Q into C, because Q is equivalent to this one. In the place of Q, I am putting this. So I will get K is equal to EC divided by P plus Q, P divided by theta 1 into 1 plus lambda by 2. This is microcoulomb here, microcoulomb per division, because K will be always in division, per division, this per division. So here what we have to, we know E, we know C, we know P, we know Q, we know theta 1 from the experiment. We only remain thing is lambda. That lambda is obtained by measuring theta 1 and theta 11. I told earlier, we are also measuring here theta 1 and theta 11 for the each value of P and Q. Okay, so from the our previous this one we already learned how we can get the value of lambda. In the previous video also I gave how to do that. So lambda will be 1 by 10 ln theta 1 by theta 11, or in terms of base log 10 to 2.303 by 10 log theta 1 by theta 11. We already learned it. Okay, that's why I am not explaining again here. In the damping correction, I told you how to do that. Okay, that calculation all we did there. So in this way, you can get the value of K. Okay, this much we have to learn in this chapter. So we are completing that third unit, and we are completing all the module of this semester. Thank you. Thank you.